Hi students, how are you? I think I have told about Hardy-Weinberg's law and its principle. You must have understood a little bit. Today I will give a detailed account of this Hardy-Weinberg's law and equilibrium. This Hardy-Weinberg's principle is also called as Hardy-Weinberg's law, and also it can be called as Hardy-Weinberg's equilibrium. Here this law is given by Thomas Hardy, a mathematician, a British mathematician, and Weinberg is a biologist. Both of them made this definition, this law regarding the population genetics, and they have studied the population. It may be human population, it may be any animal population. They studied their genetics. What are the characters in that population? What are the genotype of the population? They have done detailed study of the population genetics, right? So here the role of Thomas Hardy, mathematician, in the biology study is that he formulated this population biology in a formula form to find out the numbers of different type of individual. How we will study later on. Now you try to understand what they want to speak. They speak this definition. What they states, it states that in a large population of randomly mating, the alleles frequency and genotype frequency remains constant generation to generation in it. There should be no mutation, genetic drift, natural selection, gene migration and hybridization. So here he wants to tell that in a large population, whoever the individuals are there, if they are not migrating to somewhere else, there is no mutation, no genetic drift, no isolation, no change. They are remaining in that area. Their character means allele. Their character and their genotype, genetic constitution remain constant generation to generation. That means they don't change. Whatever character was there before, that remains constant generation to generation. That's why he told there should be no mutation, there should be no genetic drift, there should be no natural selection, no gene migration, no hybridization. If that condition is there, that population have a constant character from generation to generation. It is simple. So here I will give the explanation here. So it is the definition. I will give the explanation here. See, suppose in a population there may be 1,000, maybe 10,000, maybe lakh. So it should be large population. Small population rate, a rule ta kaam karibani. It should be a large population. So suppose I will take a population here. Suppose I am taking 5 to take account. So suppose a population having tall, the population one individual purely tall, another individual is dwarf, another individual is heterozygote, mixed, another individual is also heterozygote, another individual is also, you take another also same like heterozygote. So suppose I have taken sample, here the 5 individuals are there, their character is pure tall, pure dwarf, heterozygote tall, and heterozygote tall. Here allele means what? Allele means a single character of the individual. So here two characters are there, tallness, dwarfness. Here pure tall, pure dwarf. Here pure tall and dwarfness character is there. Here also same. So here you see what is the allele frequency. Take the tall frequency. Tall how many? 1, 2, 3, 4, 5. So tall frequency in this individual, in this population is 5. Out of how many? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 5 by 10. So that is 0.5. So allele tall frequency is 0.5 because 5 capital T in the total 10. Okay. Then what is the dwarf frequency? Dwarf allele frequency, that is 1, 2, 3, 4, 5. So here 5 by 10. So that is, it came also 0.5. So the tall frequency is denoted as P. The dwarf frequency allele is denoted as Q. So if P tall frequency P and dwarf frequency Q, in a population tall frequency dwarf frequency is 100%, isn't it? So it is 100%. 100% means that is 1. So P plus Q is equal to 1. Here P stands for a dominant allele. P stands for dominant allele. Q stands for recessive allele. Allele means character. Allele means character, tallness or dwarfness. So in a population, the PQ is always 100%. And this PQ character do not change generation to generation. Always it remains constant. 5, 5, 5, 5, 5, 5, 5, 5 like this. 5 remains like that because there is no mutation, no genetic, no recombination, nothing is there. So there is no change. That's why they remain constant generation to generation. Okay. So allele frequency remain constant. Allele frequency remain constant. Genotype frequency, how it will remain constant? Let us see. So there are individuals, TT individuals, TT individuals, TT individuals. How they remain constant? You see. Here generally in a population there are generally these 4 variety individuals will be seen. Either they may be pure tall, either may be heterozygote tall, either may be heterozygote tall, either it may be pure dwarf. Only this variety of the people individual will be seen. Other it cannot be seen. So here, if I will take TT, this is two alleles are there. Two pure alleles are there. Tall alleles, dominant alleles are there. So P stands for P. That's why P into P. T is equal to P. So TT, double T, PP. So that we can write as a P square. And another's, you see here small t is there. P stands for Q. So we can write Q. Here Q, we can write it Q square. So here okay, here okay. Then this 2 T2 are there. 2 T are there. So this will be 2 into PQ, right? So this is 2PQ is equal to 2PQ. Here in a population, pure talls are there, pure dwarfs are there and heterozygote individuals are there. So total population is 100%. In that 100%, what are there? P square there, Q square there, and 2PQ are there. So this is 100%. So 100% is 1. So here P square plus Q square 2PQ is equal to 1. Here in this way also we got PQ plus P plus Q is equal to 1. This formula, this both formula is given by Weinberg to find out the what are type of the individuals are there in the population. Here P square stands for, here you can write P square stands for homozygote dominant. Q square stands for homozygote recessive, and capital T small t 2PQ stands for all heterozygote individuals. So in that population, P square variety people will be there, Q square variety people will be there, and 2PQ variety will be there. Means homozygote dominant will be there, and homozygote recessive will be there, and heterozygote individual will be there. So by using this formula, we can find out how many numbers of what type of people are there in the population. How? Let us understand how. See, by using this formula, how we will find the number of individuals there in the population. See, here, suppose you know P stands for dominant allele, tallness, Q stands for recessive allele, right? Dwarfness. Suppose in a population, tall are there and dwarf is there. Suppose he tells in a population there are 60% of dominant tall. In a population there are dominant tall allele. Problems, huh? These problems if you do, you can understand better. So he is telling in a population, 60% dominant tall alleles are there. Find out percentage of recessive allele. So P is given 60%. Dominant tall allele P is given 60%. Q is asking that. So how will get? We know so P plus Q is equal to 1. So P is 60%. P 60% means 60 by 100. That means that is equal to 0.6. Isn't it? P value is 0.6. If you know the 0.6, then in Q you can get it easily. So that is equal to 0.6 plus Q is equal to 1. So Q will be how much? 1 minus 0.6. that is equal to 0.4, isn't it? Right? So Q is 0.4. Then he is asking, find out the percentage of recessive allele in that population. If the Q is 0.4, then 0.4 means what? What does it mean? That is 40 by 100. So that is equal to 40%. So Q is, so there are 40% recessive allele. So 60% dominant allele and 40% recessive allele. In that way, we can find out the type of individual, type of alleles, the number of alleles present in a particular population by using this Hardy-Weinberg's principle and Hardy-Weinberg's formula, that is P plus Q is equal to 1. Right? So, by that way also we can find out the individuals, type of individuals present in the population. And to find out that, we have the P square, Q square plus 2PQ like that. That is 1. If you once you know the value of PQ, once you know the value of PQ, then you can also find the value of the P square, Q square by squaring it, and PQ multiply and multiply into 2. You can find it out. So it is easy. Let us see one problem out of this formula. See, suppose it asks in a population, another question it may ask, in a population 81% of dominant, 81% dominant homozygote present. 80% homozygote present. Find out percentage of recessive homozygote. So here dominant homozygote, here homozygote dominant P square is 81%. That means 81 by 100, right? That means 0.81, right? So P square is equal to 0.81. So P will be how much? 0.9, right? 0.9, P is equal to 0.9. If P is equal to 0.9, then P plus Q is equal to 1. So how will you know? P is equal to 0.9 plus Q is equal to 1. So Q will be how much? 1 minus 0.9, that is equal to 0.1. So Q is equal to 0.1. If Q is equal to 0.1, then Q will be how much? 1 by 10 by 100, 10%. Isn't that it? Am I okay? So Q is equal to 0.1, then Q will be how much? 0.1 by 100. 0.1. So 0.1 means how much? 0.1 means how much? That is 10%. 0.1 means that is 10%. Isn't it? So, am I right? So, but Q value is the 0.1. So, if the Q value is the 0.1, then Q square is how much? Am I okay? So, 0.1 Q square will be 0.1 into 0.1. That will be how much? 0.01. Okay. 0.01. Then 0.01 q square, 0.01 we can write it. How much? 1 by 100, 1%. Okay. So 0.1, 0.1 is equal to 0.01, 0.01 is equal to 1 by 100. So that is equal to 1%. So q square is the homozygote recessive. This is the homozygote recessive. Right? So he asked to find out the percentage of recessive homozygote. So recessive homozygote will be 1%. If there is a 81% of homozygote dominant, then the recessive homozygote will be 1%. Suppose if you again you will ask also find heterozygote percentage. How will find? So heterozygote is how much? Heterozygote individual is 2pq. So this is 2 into pq. So p is how much here? 0.9. 2 is equal to 2 into 0.9 and q is equal to 0.1. So how much will be there? 18.18. Right? So this is called, this can we can write as 18 by 100. So this can be, we can call it 18%. So 2pq is 18%. q square, जोटा कि homozygote recessive is how much? 1%. 1%. And p square is equal to how much? 81%. So p square, q square, 2pq total, how much population will be? In a population, p square homozygote dominant will be 80%, homozygote recessive will be 1%, and heterozygote will be 18%. So total you see 1, 1, 2, 8, 10, 2, 8 to 10, 1, 8, 1, 9, 1, 10, 100%. See, p square, q square, 2pq is 100%. Here, so in this, by using this formula, we can find out what type of, how many percentage of what type of individuals are there. So we can find out through this formula. Right? By any type of problem, we can find out by using this Hardy-Weinberg principle. Okay? Thank you.